This is the Amateur Logician from amateurlogician.com. I hope you are doing well. We're going to continue our exploration of inductive logic and think about Bayesian probability. We're going to work through 2 example problems. But before we do that, I think we should do some derivations. Let's compare and contrast. Let's think about the probability of P given Q versus the probability of Q given P. So these are converses of each other, but they need not necessarily be equal to each other. Now, Bayes' theory will allow us to calculate a probability with a converse. That's one of its powers. And we're going to derive this formula, kind of like we derive the various probability calculus rules. So first, note that the probability of P given Q is equal to the probability of P and Q divided by the probability of Q. And that is, so to speak, by definition of a conditional probability. Second, the probability of P given Q is equal to the probability of P and Q divided by the probability of P and Q that or not P and Q. Why is that? Here we're going to resort to propositional logic because the proposition Q is logically equivalent to the proposition P and Q or not P and Q. So this is a logical equivalence. And we can prove that, for example, with the so-called truth table, which we won't do here. Third, the probability of P given Q is equal to the probability of P and Q divided by the probability of P and Q plus the probability of not P and Q. So that's the disjunction rule. And here we have independent events. So it's a special disjunction, or we can say the special disjunction rule. That's why we can justify the move from 2 to 3. And for our fourth step, we can say the probability of P given Q is equal to the probability of P times the probability of Q given P divided by the probability of P times the probability of Q given P plus the probability of not P times the probability of Q given not P. And here we're resorting to the general conjunction rule. We have thereby proved the formula for Bayes' theorem. Now this formula can be further generalized. Right now this formula just deals with 2 statements, 2 propositions, so to speak, or events, P and not P. Now we're going to utilize that formula for our 2 example problems. So let's consider example 1. So we're told that the probability a person in the city has illness X is 0.01. Now, if a person actually has that illness X, then the probability it will be detected is 0.96. And if they do not have X, then there is a 0.03 probability that there will be a false positive. Given that a person is diagnosed as having X, illness X, what is the probability that they actually have it? So let's think about what is given first. So we're given that the probability of a positive test given having illness X is equal to 0.96. Okay. We're given that the probability of a negative test given not having X is 0.03. So we're given that. We're given that the probability of having X is 0.01. And finally, we're given that the probability of not having X is equal to 0.99. That's just based on subtraction, right? Okay. So we're going to utilize that formula. We're given this stuff here. So the probability of having X given a positive test is equal to what? Well, it's going to be equal to the probability of having a positive test given X times the probability of having X divided by the probability of a positive test given X times the probability of having X plus the probability of having that positive test given not having X times the probability of not having X. So that, if we just plug in our value, so to speak, so we have that 0.96, so we have this here, times a 0.01, this here, divided by the 0.96 times the 0.01 plus a 0.03, it's right here, times the 0.99, this right here. So then we can plug that into a calculator, and we're going to get approximately 0.244. Okay. And we can also ask, if you don't have it, let's say we don't have it, well, we'll just say 1 minus the 0.0244, so approximately 0.756 probability that you don't have it. So not too bad. Let's try the next example. So we have 3 machines. We have machine A, B, and C. Machine A produces 1/5 of some total production process, so to speak. B produces 1/2, and C produces 3/10 of the production processes. We're told that A's defective rate is 10%, B's is 5%, and C's defective rate is 6%. By random selection, a part is found defective. What's the revised probability that it came from machine A? So a key aspect of Bayesian probabilities is how does the probability of some event change based on this newly obtained information, this revised information. Okay. So we have machine A, B, and C. We should think about our proportion part, so to speak. We should think about our percentage of defects, right? Or defectiveness. or defectives. Well, yeah, whatever you want. Percentage defectives, I guess, would work. And we should think about the probability of the part times the probability of the defect. We're told that A is 1/5 of the proportion of this production process, that B is 1/2, and that C is 3/10. And the percentage of being defective, so A, we're told is 10%. We're told that B is 5%, and we're told that C is 6%. That's just given. So now we just multiply, okay? So the probability of the part and the probability of being defective. So we'll get 0.020 for A, 0.025 for B, and 0.018 for C. And then we can think about the sum, right? If we're adding that up as 0.063. And let me try to erase some stuff here. And hopefully we'll have enough room without erasing more stuff. We're thinking about the probability of a given being defective, okay? So it's going to be equal to the probability of A and being defective divided by the probability of being defective, right? So we know that this here is that 0.02, and we know the probability of being defective is that 0.063, and so we have our 0.02 over our 0.063. Throw that into a calculator, we get 31.7% probability. So that answers our second example. Now, I am the Amateur Logician from amateurlogician.com. Hope this video has been helpful. We took a look at Bayesian probability. We very briefly derived a general formula, although this formula here can be extended to an even more generalized format. But in any case, we derived our formula that fits our purposes here, and we worked through two practice examples. If you enjoyed this video, please consider giving it a like. A lot more is ahead on this YouTube channel. If you haven't already, please consider subscribing to this YouTube channel and visit my website at amateurlogician.com. You will find an extensive tutorial on traditional verbal style logic there. Thanks for watching. Good luck to you and be well.